Thanks. Where are you headed?
Celeste is having diarrhea. She didn't have the diarrhea pills with her, so I'm taking her some.
All right.
Have them in her pocket. She ate salami and cheese when she got to work. That's not an elimination diet, you know?
Okay. Great. I'm waiting for the view screen to pop up here. Good morning. I don't know if you can hear me yet. All right. Okay, I see Adam, Kaylee. Beautiful. I've been getting your work. I really appreciate you sending it to me. It'll make your progress reports look really good here. Due tomorrow. Social distancing emojis. Very good. Very good. Okay. We're fortunate in that we don't have a whole lot of problems to do today. For some reason. Okay, yeah, that's right. I don't know where they're showing the total amount of time there. Yeah, that's odd. Okay. All right, let's go to the even number problems. Where you headed? Okay, here we have Here we have 18, which is for b equals 2. So your basic form of an exponential function is this. F of x, I'm going to get my little skinnier pen. Fx equals a times b, and in this case b is equal to 2, right? And we're going to have to the power of x minus h plus k. And here we have our horizontal asymptote at y equals 3, so k is equal to 3. This h is equal to -1. So that means that our basic function is going to be f of x equals a times 2 to the power of x minus -1. So that's going to be x plus 1. And then we're going to have plus 3. And now we're going to take our reference point in here, which is -1, 5.2, and I'm going to do a color code change just to be different, I guess. And so we have f of x, which is 5.2. We get it from this first reference point, equals a, which we don't know yet, times 2. So we have -1 plus 1 plus 3. And 2 to the -1 plus 1. Well, let's do some things at a time here. We'll subtract 3. So on the left side we have 2.2 equals a times 2 to the 0 power. Well, 2 to the 0 power is 1. So basically 2.2 is equal to a. And so we know based on having what a is, we know that our function is going to be f of x equals 2.2 times 2, and I'm just going to put 2 in parentheses, times x plus 1, and it'll be plus 3. So that's going to be it. Now the only thing, a couple things to do left, we're going to substitute in our other reference point to see if it works out. And so we have 0, 7.4. So I'm going to put here 7.4 is equal to 2.2, and we're just seeing if this works out, times 2 to the power of, we have 0 plus 1, so that's going to be 1 plus 3. And we'll just continue working on the right side. We have 2.2 times 2, which is 4.4, plus 3 equals 7.4. Check. So this is going to be a valid function for us. And then we have, we're asked to find the domain and range in set notation. So our domain is going to be what it is for all exponential functions, which is x such that x I'll just write it like this: negative infinity is less than x, which is less than positive infinity. So that's going to be our domain. And our range is going to be, we have our k values 3, so range y such that y is greater than 3. That's a 3. Okay. So here's our domain and range. So that's it. Okay. That wasn't too hard, was it? Okay, next we go to 20. And in the case of 20, we have this steep up graph here. So our basic function here for b is going to be f of x equals a times b to the power of x minus h plus k. And so our first reference point is this one here, negative 3, comma, negative 4.4. And our horizontal asymptote is y is equal to negative 6. And we have h is going to be equal to 3, because that's a transference of the point 0, comma 1. So what we're going to have here is f of x equals a, which we don't know yet, times 10 to the power of x minus h, which is 3, plus k, and k is negative 6. So this is what we have here. And we're going to take our point -3 or 3 comma -4.4 and just write that in place. So we have -4.4 is equal to a times 10 to the 3 minus 3 minus 6. And if we add 6 to both sides, we get on the left side 2.4, and then we have 10, we have a times 10 to the power of 0, and 10 to the power of 0 is 1, so that's going to be a. So a is equal to 2.4. Okay, so now we can, so our function, if it works out right, is this. It's going to be f of x. We're going to test it on that second point here in a minute. Equals 2.4 times 10 to the power of x minus 3 minus 6. And now we're going to try out our second point, which is 4 comma 10. So I'm going to do that up here in red. I'm going to put 10 is equal to 2.4 times 10 to the power of 4 minus 3, and we're going to be minus 6 out here. So when we add 6, on the left side we get 16. So 16 should be equal to 2.4 times 10. Somehow that is not right, is it? Because 2.4 times 10 is 24. Let's see. Something is messed up. I worked it out yesterday. It was great. Yeah, A should be 1.6. Boy, I'm having some problems. Yeah, that's what it is. You didn't call me on it here. It's just my arithmetic here was bad. So this is it. This is 1.6. That's why we do our checking. So this is 1.6. This here is 1.6. Yeah, 1.6. So 1.6 times 10. So 16 equals 16. Check. So this is a real-time example of why you check your reference point. Okay, your domain is going to be same as we've done before. X such that x is greater than -infinity but less than infinity. And range we have y such that y is greater than our horizontal asymptote, which is -6. Occasionally I'll make mistakes intentionally. This was not one of those times. But I hope it showed you that using your test point is really crucial in determining potential mistakes. Okay. Next. All right, now we're to the real world uses of exponential functions, which can be really quite helpful. What we have is Sue has a lamp from her great-grandmother. She has it appraised and finds it is worth $1,000. She wants to sell it, but the appraiser tells her that the value is appreciating by 8% per year. In how many years will the value of the lamp be $2,000? So what you're looking for here is, I'm going to write down your basic exponential function where a rate is involved. A of t, so t is going to be our input variable, so a stands for amount, is equal to a sub 0. And a sub 0 is your starting amount times 1 plus r to the power of t. Okay, so that's really it. Now, in this case, r, you're given a value of r is 8% per year. And what you want to do is rewrite your percentage as a decimal. So 0.08 is what you're going to have. So what you have is a sub t, a of t, is equal to our starting value, which is $1,000 times 1 plus, now an error people make sometimes is to just put 8 in here instead of 0.08. We got to put our decimalized value here to the power of t. And in this particular case, we're given that we want to appreciate to 2,000, so we can rewrite this as 2,000 equals 1,000 times 1.08 to the power of t. Now we can solve for t using logarithms. When logarithms is where we're going to be going in a couple weeks, exponential function logarithms. But what we're going to do is solve this equation by graphing, and we're going to write down two separate equations here and find where they intersect. We're going to put y1 is equal to 1,000 times 1.08 to the power of x, and we're going to write y2 is equal to 2,000. So let's go to our calculator, and I'm going to clear out of here, go to our function editor. So we put in y1, 1,000 times 1.08 to the power of x, and then for y2 we're going to put 2,000. And when we graph this function, this is what we get. Don't see a heck of a lot. Why is that? Well, the reason is because our y-intercept here is 1,000 for this y1 and 2,000 for our y2. So we're going to go to our window and fix that. We're going to start at time 0, and I don't know how long it's going to take to get there. I'm going to raise that up to x max of 15. Y minimum, we can leave at -10, but we want to have our y maximum of at least 2,000, so I'm going to put 3,000 here. And I'm going to put my y scale of 100, I guess. So really we should have everything here. We graph. We see y1 in blue and y2 in red. And so to find out what's happening, we go to second, trace, 5, enter, enter, enter. So we get, looks like about intersection x equals 9.006. That's going to be like 9.01 years. Okay, so about 9.01 years, or 9 years. For some reason, the book gives like 9.04 years, but that's what it is. So basically what you have, this 1 plus r, this is what the base is. That's our base. And next week when we get to exponential decay functions, it's going to end up being 1 minus r, or 1 plus a negative number, so we'll get a base of less than 1. But when you have a base of greater than 1, you do have exponential growth. Okay, let's go over to 24. Bill invests $3,000 in a bond fund with an interest rate of 9% per year. If Bill does not withdraw any of the money, in how many years will his bond fund be worth $5,000? Well, it's the same format here. We have a sub t equals a sub 0 times our base, which is 1 plus r to the power of t. And here we have r is equal to 9%, which is equal to 0.09. And so just writing this out quickly, if we have, we know we want to get to $5,000, right? So $5,000 is equal to 3,000 times 1 plus 0.09, so it's going to be 1.09 to the power of t. So we're going to be looking at our y1 is equal to 3,000 times 1.09 to the power of t, and y2 is equal to 5,000. So let's go to our calculator. Now, I invite you, as we're going here, I'm running probably, the feed is running at least 30 seconds behind. So I want to make sure you ask me any questions you can, because we're getting toward the end of this right now. So make sure you ask questions or say hello. Glad to see Adam and Kaylee already. So 5,000. And it's going to be pretty much the same thing. We have a window already set up, but we know we're going to we need to have our Y max at least 5,000. So if I go to a window here, I'll leave X max the same. I hope that's long enough. And Y max, we need at least 5,000. So I'm going to make this 6,000 instead. And see how that works out. Okay, we graph. Okay, that looks good. What you're looking for is just an intersection point. And then this little keystroke chant I want you to have in your mind. Second, trace, 5, enter, enter, enter. And you do that, we get 5.9. So T is equal to, about 5.93. We'll go to this 5.93 years. And let's see if the book has this. I'm sure it does. Yeah, they gave 5.96. I think they're rounding off more than I am. Now, in pre-calculus, we're going to be doing this the first semester next year in pre-calculus, and we're going to be using these money type exponential monetary growth. We're going to use compounding periods and also continual compounding, which is using the letter E. Anyway, so that's our answer for 24. And lastly, we're going to go on to 26. Explain the error. And really, in explaining the error, we're looking at what we did looking at problems 22 and 24. Okay, a student has a baseball card that is worth $6.35. He looks up the appreciation rate and finds it to be 2.5% per year. He wants to find out how much it will be worth after 3 years. He writes the function f of t equals 6.35, and so this is going to be, in the way we looked at our problems earlier, that's going to be our a sub 0. And this 2.5 is going to be our base. But how do we figure the base? The base is equal to 1 plus r. In this case, that's going to be 1, and r is 2.5, so we're going to have 0.025, which is going to be equal to 1.025. One thing to look for in monetary growth, usually for annual, it's going to be usually 1.0 something. So if you see something that like 2.5, you realize that isn't right. So what did the student do wrong? Well, the student used base of 2.5 instead of the correct base, $1.025. So we're going to write this as, and we want to know after 3 years, Aristoteles Socrates Moreno. Very good. Good to have you. May I call you Aristotle? That would just be easier for me. Equals, we're starting out with 635 times 1.025 to the power of 3. So we can just go to our calculator and put in, I'll get a page here. So it was, what was it? 635? Yeah, 635. .025 to the power of 3. So $6.838. So $6.84. So really, that's it. So really, these are all the even number problems worked out from the assignments of this week. Are there any other questions? I'll just wait here for a minute for lag before I sign off. Good to see everybody here. Adam, Kaylee, Aristotle. Anything? Yeah, I'm noticing the lag on this is quite a bit. Okay, well, good. We'll just call this a session. I appreciate everybody being here, and I will let you know what's going on next week for our exponential decay. Take care. Bye-bye now.